At first, there was an infinitely dense mass of matter, which went through a tremendous explosion that led to the formation of atoms, molecules, stars, and galaxies, structures we observe today. For many years, this has been the explanation put forward by physicists. However, recent research suggests a new perspective. The universe may not have had a singular beginning as once thought, but could instead be part of an ongoing cycle, where the universe expands and contracts in an infinite loop. Brian Cox, a renowned physicist, expresses skepticism about the theory of a primordial cosmic explosion, arguing that something cannot come from nothing. This challenge adds a fascinating element to the debate. Additionally, data from the James Webb Space Telescope has revealed findings that challenge the idea that the Big Bang marked the definitive beginning of the universe. This raises a crucial question. If the Big Bang wasn't the start, what was? Join us as we explore the origins of the universe, delving into the mysteries beyond the Big Bang and searching for answers to this and other fundamental questions. If you're interested in staying updated on news about the universe and its mysteries, be sure to subscribe to our channel. Hit the like button, share the video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe's early stages, known as the Big Bang theory. According to this model, the universe was once much smaller, hotter, and denser than it is today, around 13.8 billion years ago. During this period, all the elements that make up our reality were formed in mere minutes. In this theory, our universe, including stars and galaxies, was once as tiny as a peach and had an incredibly high temperature, over a quadrillion degrees. Interestingly, this remarkable story aligns perfectly with current observations. Astronomers have studied everything from the leftover electromagnetic radiation of the early universe to the abundance of the lightest elements, and found that it all agrees with the predictions of the Big Bang. To the best of our knowledge, this depiction of the universe fits reality perfectly. However, despite its apparent robustness, we know that the Big Bang theory does not explain the full picture. There remains a missing piece of the puzzle, specifically in understanding the very first moments of the universe. This challenge is largely due to the limitations of the physical theories we currently use. The combination of general relativity and high-energy particle physics provides a significant theoretical framework, but as we delve deeper into the universe's initial moments, the mathematical complexity increases dramatically, reaching a point where our current methods cannot provide meaningful solutions. One sign of this problem is the presence of a singularity, a point of infinite density, at the start of the Big Bang. This suggests that the universe was once compressed into an infinitesimally small and dense state, which seems illogical. To address this challenge, we need to explore new frontiers in physics and develop approaches that surpass these limitations, offering a more complete understanding of the universe's origin. Our current tools and theoretical frameworks are not sufficient to tackle this problem, so we must develop new physics capable of explaining gravity and the other fundamental forces at extremely high energies. This is where string theory comes into play. String theory seeks to provide a physical model capable of unifying gravity with the other fundamental forces, particularly at ultra-high energies. In this theory, the concept of an erotic universe arises, named after the Greek word meaning design or fire. This idea suggests that the Big Bang, as we know it, was the result of a prior event, meaning it wasn't the absolute beginning but rather part of an ongoing cycle. Expanding the concept of an erotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for centuries, string theory provides a solid mathematical foundation for this concept. In cyclic cosmology, the universe functions as if it endlessly alternates between phases of expansion, Big Bangs, and contraction in an infinite cycle, extending far into both the past and the future. This theory was proposed by the renowned physicist Roger Penrose, who was awarded the Nobel Prize for his work. Penrose became intrigued by a unique mathematical relationship between the early universe, described by extreme density, temperature, and compactness during the Big Bang, and the future state of the universe, which is predicted to be incredibly cold, extended, and devoid of matter. The theory suggests that these two states become mathematically indistinguishable when taken to their extremes. Though it might sound perplexing, the complete absence of matter could be the driving force behind the creation of all the matter we observe today. From this viewpoint, the Big Bang originates from what is almost nothing, After all the matter in the universe has been consumed by black holes that eventually dissipate into dispersed photons in an enormous void, the universe emerges from what, from another perspective, essentially amounts to nothingness. However, this nothing is still a form of something, a physical universe, albeit an empty one. The key lies in how the same state can be interpreted as both a cold, empty universe and a dense universe, depending on one's perspective. The secret to this interpretation lies in a complex mathematical method called conformal transformation, which is a mathematical change that adjusts the size of an object while preserving its shape. Roger Penrose demonstrated that the void state and the hot, dense state can be connected through this scale change, adjusting their spatial and temporal patterns despite their differences in size. However, Penrose argues that the concept of size loses its meaning under these extreme conditions. In cyclic cosmology, the sequence of events progresses from an old, cold state to a young, hot state. The existence of the hot, dense state is the result of the previous cold, empty state. However, this causal relationship doesn't follow the traditional pattern of time, as both size and time lose their conventional meanings in these extreme conditions. The cold, empty state and the hot, dense state exist on independent timelines, meaning that from the perspective of an observer within their own time frame, the cold, empty state could continue indefinitely. Physics and philosophy intertwine in this domain of cyclic cosmology, as the theory provides speculative and detailed explanations for the origins of these cycles. Nevertheless, even if Penrose's ideas gain support from cosmological advancements, a deeper philosophical question remains. What is the origin of physical reality itself? How did these cycles come into existence? This leads us to ponder the justification for the existence of something rather than nothing, one of the fundamental metaphysical inquiries. For the purposes of this discussion, we will focus on explanations when investigating the origins of these processes,
and there are three possible answers.
There are several possible outcomes to consider. First, there might be no clear reason at all. Second, there could be an infinite series of cycles, where each cycle represents a different universe, with the initial quantum state of each universe being determined by some characteristic of the preceding universe. Finally, it's possible that the cycle is singular, within a repeating universe, where the beginning of each cycle is explained by some feature of its own end. These possibilities are appealing because they avoid the need for uncaused events and provide a more complex explanation within the framework of physics itself. Roger Penrose suggests the idea of an eternal series of cycles influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose proposes that each cycle is influenced by random quantum events that cause variations between cycles. This concept opens up exciting possibilities for experimental physicists, as it suggests the potential for detecting subtle traces or anomalies in the cosmic microwave background radiation from the Big Bang. The study of cosmology and the origins of the universe continues to captivate scientific inquiry, pushing the boundaries of our understanding beyond the realms of known physics and into the speculative territories of theoretical structures. At the heart of these questions is the pursuit of unraveling the mysteries surrounding the beginning of existence itself. How did the universe come into being? And what processes governed its evolution from inception to its current state? One enduring idea that has intrigued cosmologists is the multiverse hypothesis. This theory posits that our universe is just one of an infinite number of universes, each with its own distinct physical laws and properties. The multiverse hypothesis arises from the framework of quantum mechanics and inflationary cosmology, suggesting that during the rapid expansion of the early universe, pockets of spacetime could have undergone separate expansions, leading to the formation of distinct universes with differing attributes. Inflationary cosmology has become a cornerstone of modern cosmological theories, offering a compelling explanation for the large-scale structure of the universe and the uniformity of cosmic microwave background radiation observed today. According to inflationary theory, a brief period of rapid expansion, known as cosmic inflation, occurred in the fraction of a second following the Big Bang. This dramatic expansion stretched the fabric of spacetime, smoothing out irregularities and setting the stage for the development of galaxies and other large-scale structures. While inflationary cosmology has successfully addressed numerous observational puzzles, such as the horizon problem and the flatness problem, it also raises intriguing questions about the nature of the universe after inflation. Some theories suggest that inflation could be eternal, with new universes continually emerging from quantum fluctuations within an ever-expanding multiverse. This idea challenges traditional notions of a singular, linear cosmological history and invites speculation about the broader implications of a limitless and diverse cosmic landscape. The concepts of dark matter and dark energy continue to fascinate cosmologists, as they account for a significant portion of the universe's mass-energy content, despite being largely invisible and elusive to detection. Dark matter, inferred from its gravitational effects on visible matter, suggests the existence of a form of matter distinct from the ordinary matter that makes up stars, planets, and galaxies. Its gravitational influence plays a crucial role in shaping the large-scale structure of the universe. In contrast, dark energy is believed to be responsible for the accelerated expansion of the universe, observed in recent astronomical studies, such as those measuring the distances to distant supernovae. This mysterious force counteracts the gravitational pull exerted by matter, causing galaxies to recede from one another at an accelerating rate. The nature of dark energy remains one of the most pressing questions in cosmology, with profound implications for the ultimate fate of the universe, whether it will continue expanding indefinitely, eventually collapse, or undergo a dramatic transformation into a new phase. Cosmologists also grapple with the concept of the cosmic microwave background, CMB radiation, which serves as a remnant of the early universe, originating from a time approximately 380,000 years after the Big Bang. Detailed measurements of the CMB have provided crucial insights into the composition, age, and geometry of the universe. Tiny fluctuations in the CMB temperature across the sky offer glimpses into the seeds of structure formation, providing evidence that the universe began in a hot, dense state and gradually evolved into the complex cosmic tapestry we observe today. Beyond observational astronomy, theoretical physics continues to explore ambitious frameworks, such as M-theory and quantum gravity, with the aim of unifying the fundamental forces of nature and reconciling the principles of general relativity with those of quantum mechanics. M-theory, an extension of string theory, suggests that the universe may consist of higher-dimensional structures known as branes, offering a potential resolution to long-standing puzzles in particle physics and cosmology. Quantum gravity, on the other hand, seeks to describe gravitational interactions at the quantum scale, where traditional concepts of space and time break down. This field of research remains highly speculative, with implications for understanding the behavior of black holes, the early universe, and the fundamental nature of physical reality itself. The quest for a theory of everything, a framework that encapsulates all known physical phenomena within a single coherent structure, remains a central goal of contemporary theoretical physics. Such a theory would not only unify the forces of nature but also offer deeper insights into the origins and evolution of the universe, from the smallest subatomic particles to the vast cosmic structures spanning billions of light-years. Philosophical inquiries into cosmology also raise important questions about the nature of existence and our place in the universe. The anthropic principle, which suggests that the universe's physical constants and conditions are finely tuned to support the development of intelligent life, invites speculation about whether the universe was designed with a purpose or whether our existence is a fortunate byproduct of cosmic evolution. The study of cosmology also intersects with broader philosophical debates about determinism versus free will, the nature of causality, and the possibility of multiple universes with different physical laws. These discussions reflect humanity's enduring curiosity about the origins of the universe and our place within it, prompting reflections on the limits of scientific knowledge and the boundaries between the observable and the speculative.